Hi all! In this video, we're going to begin our discussion about confirmatory factor analysis, the CFA. We use CFA to test some postulated relations between the observed variables, the indicators, and the underlying construct, the latent factors. We know the measured variables, and we also have a pretty good idea about the underlying factors. Supported by theoretical evidence, in CFA, we hypothesize the relationships between the measured variables and the underlying factors. Then we collect data to test how the hypothesized model structure is supported by the empirical evidence. Remember that in EFA, the underlying constructs are discovered based on the observed data structure. Therefore, every variable is related to all underlying factors. In other words, there is a factor loading for every pair of variable and factor. However, in CFA, we're working with a theoretically derived model. Therefore, in the proposed model structure, a measured variable only has a loading with the underlying construct it's hypothesized to measure, but no relationship with other latent factors. This diagram shows a very simple CFA model. It has one underlying factor and three observed indicators. The direction of the lines makes it clear that the underlying factor is the cause of the variations observed in those variables. That is, we hypothesize that people with depression will show signs of pessimism, irritability, and insomnia. Observed variations in those three behavioral symptoms are caused by the level of depression. Because the observed variables are imperfect measures of the underlying construct given their unique error components, the source of variation from the unique random and systematic errors are also marked on the diagram for each observed indicator. The type of relationships you observed in this diagram from the latent factor to the observed variables is called reflective measurement. Sometimes you encounter a different type of diagrams in which the factor is a composite of measures that might covary. A good example is the SES. People are so used to quantify the SES with family income, parents' education. However, SES is not a cause of those factors. This is called the formative measurement with cause indicators. Formative indicators can be handled in M+. However, given the purpose and usage of CFA in the context of SEM, using formative indicators is not encouraged, and we will limit our discussion to only reflective measurement in this course. Here you have the notations commonly used in a CFA model. There are two latent factors represented with oval shapes, 6 measured variables in the rectangular shapes. The direction of the relationships indicates the underlying factors are the causes, the observed variables are the effect indicators. In unstandardized CFA models, we need to estimate the variances of the latent factors as well as the variances of the error components for the observed variables. In a CFA model, all latent factors are correlated unless specified otherwise. In most cases, because those error components are unique, there are no correlations between them. But in some special cases, you have a reason to believe some of the error components are correlated. then you use this line to show the correlation between them. Now let's look at the decomposition of a correlation matrix for a standardized CFA model. I'm going to use the same depression example here. First, let's be clear that the observed indicators are the effects, so they will be the dependent variables in your structural equations. The latent factor is the only causal factor for all the observed variables, so you only have one independent variable in each of your structural models. The factor loadings are PV1F1, PV2F1, and PV3F1 respectively for the three indicators. For this CFA model, we have three structural equations because there are three observed indicators. V1 equals PV1F1, the factor loading, times F1, the factor, plus E1, the error component. Similarly, for the other two, it's V2 equals PV2F1 times F1 plus E2. V3 equals PV3F1 times F1 plus E3. Because there are three observed variables, we have a 3 by 3 observed correlation matrix. For the model implied correlation matrix, the correlation between V1 and V2 is simply PV1F1 times PV2F1. Correlation between V1 and V3 is the product of those two factor loadings. Similarly, for V2 and V3, the correlation is the product of those two factor loadings. In this CFA model, there are three unknown parameter values. They are the three factor loadings. And based on the model implied and observed matrices, we can have three equations. So this is a just identified model, and solving those three equations, we can get the parameter values. And the result here show that from depression to V1, the factor loading is 0.50. From depression, the underlying factor, to V2, the factor loading is 0.6. And the factor loading from depression to V3, insomnia, is 0.70. If you are curious why the error component E1, E2, E3 are not unknown model parameters for estimation, I have an answer for you. Because we're working with a standardized CFA model, all observed variables have a variance of 1. The explained variance of an observed variable is simply the squared value of its factor loading. Once we know the value of the factor loading, 1 minus the squared value of the factor loading gave you the error variance. For example, the factor loading from depression to pessimism is 0.50. Square this value, you get 0.25, which means about 25% of the variance in pessimism can be explained by this depression underlying factor. 1 minus 0.25 gave you 0.75. That means about 75% of the variation for V1 is from those random and/or systematic errors. For an unstandardized CFA model, the decomposition of the variance-covariance matrix is a much more complex matter. The structural equations stay the same, except that the unstandardized factor loadings are used. We know that there are 6 unique values in the observed variance and covariance matrix. We follow the same rules as in past analysis to decompose the variances and covariances here. To decompose the variance of an observed variable, you go back this factor loading BV1F1 times CF1 and come back by times PV1F1 again, then plus the variance of the error component. We have it right here. Similarly, for the variance of V2, it's BV2F1 squared times CF1 plus CE2. And for variance of V3, it's BV3F1 squared times CF1 plus CE3. The covariances are simple too. So BV1F1 times CF1 times BV2F1 is a covariance between V1 and V2. And you can do the same thing for the other two pairs. The decomposition of the variances and covariances gave us this model implied matrix. By relating the model implied matrix to the observed matrix, we will have 6 equations. And here comes the problem. There are 7 unknown parameter values to estimate. They include the variance of the underlying factor, the 3 factor loadings, and the variances of the 3 error components. 7 is greater than 6. We have an under-identified model, and a solution is not possible. Here is why. In order to solve those 6 equations, we need to have either a standard deviation or a variance value for the latent factor. However, because the latent factor is not observable, we do not have any scores on it. Given the dilemma, a solution is only possible if we assign a unit of measurement to the underlying factor. 2 different strategies has been adopted in order to give a measurement scale to the latent variable. The first one is called the unit variance identification, the UVI. It standardizes the latent factor and sets its variance to 1. With CF1 equals 1, now we have 6 unknown values and 6 equations. This CFA model becomes just identified and a solution can be found. In the second solution, a reference variable is chosen. The latent factor is set to have the same measurement scale as the reference variable. As shown in this example, pessimism is chosen as the reference variable. Its factor loading is set to 1 so that depression, the underlying factor, can share the measurement scale with pessimism, the observed reference variable. Again, we have 6 unknown values in 6 equations, and this model becomes solvable. Even though both strategies usually result in same overall model fit, the second strategy of choosing a reference variable is recommended. One reason is because that variance and covariance matrix are used more often than correlation matrix in SEM. Also, unit variance identification is inappropriate when comparisons are made between groups or across times. Now, both standardized and unstandardized CFA models are solvable. Let's talk about the interpretation of the parameters. In standardized CFA models, the factor loadings are also called pattern coefficients. They are interpreted as the correlation between the measured variables and the underlying factor. The unanalyzed associations, such as the correlations between the underlying factors, are simply interpreted as correlations. In unstandardized CFA models, the unanalyzed associations between the underlying factors are covariances. We interpret the factor loadings the same way as we interpret unstandardized regression coefficients in multiple regression. Be careful that the explained variance of an indicator is no longer the squared value of that factor loading. The unexplained variances will be estimated as part of the model parameters. So the explained variance of an indicator is its total variance minus its unexplained variance.